Welcome back. Well, let's take a look at an actual situation involving Newton's law of cooling. So let's let Y represent the temperature in degrees Fahrenheit of an object in a room where the temperature is kept constant at 60 degrees. Now, that's a little bit cooler than normal room temperature. But now our hot object is going to cool from 350 degrees to 200 degrees in 10 minutes. Now, 350 degrees, that's a common temperature to bake something in your oven at. So let's say you took something out of your oven at 350 degrees, and now after 10 minutes, it's cooled all the way down to 200 degrees. The question, though, at the end is how much longer will it take to cool all the way down to 100 degrees? Okay, now, so this situation implies we're using Newton's law of cooling, and you can go ahead and right away go and use the model we derived in the last video, that the difference in the two temperatures is always following exponential decay, a e to the kt. Or in fact, you could even go further and write y equals the air temperature plus the a e to the kt. Okay, that's actually where you should probably start. Also, remember in the last video, it was noted some important characteristics that are always provided in the problem. For example, we know that the air temperature is given, it's 60 degrees. I would also, if you watched the first video, I'd like you to take a moment and remember what we know about the constant capital A, the one we're going to put right there. I would encourage you to pause the video and just think about that for a minute. There is enough information in the description of the problem to know what that is. Okay, so in the last video, we learned that if you look at the equation that I first wrote, and we know that if t were 0, the whole right side would be capital A, and the left side would be the difference of the two temperatures that are in use in the problem. The starting Y value, which is given to us, the starting temperature was 350 degrees, and the room temperature is constantly 60 degrees. So using that knowledge, the capital A constant is going to be 350 degrees minus 60. So in other words, 290 degrees. So I already know two of the three constants in my equation. I know that the air temperature is 60, and this capital A is now going to be 290, and I still don't know the constant K, but we'll get to that next. Okay. I have the other temperature information that after 10 minutes, the temperature was 200. So we're given two ordered pairs in the problem, if you think about it. Okay, at the time 0, the Y value of the temperature was 350 degrees. And then secondly, after 10 minutes, the temperature was already down to 200. And then what we're going for really is going to be how long until it was down to 100. Okay, but we won't know this until we actually have this model completed. So the next job is to take that second ordered pair and solve for the constant K, right? So when the Y value is 200, and I'll fill this in, and the time will be 10. It'll be e to the 10k. And now we're just going to solve this exponential equation. So we'll subtract 60 from 200, and it'll make 140 equals 290 e to the 10k. We'll have to divide by 290. The only thing I'm going to do to reduce it for now is divide out by 10. So it'll be 14. I'm going to leave that as 14/29 equals e to the 10k. And I think you probably know where we're going from here. It's going to be, we have to take the natural log of both sides, and we'll be dividing that by 10. So my final value for k is to take the natural log of the fraction 14/29, and then we're going to divide that by 10. Now you saw, if you watched the videos from Monday, you saw us take things like this and store it in our calculator. This is a good time to do that again. So I'm going to grab the calculator. I'm going to find the natural log of the quantity 14 divided by 29. And then we're going to divide that by 10. And that's my K value. Now it is negative because in exponential growth and decay problems, when your constant K is negative, it causes your growth to be decreasing, right? So that's okay. We have a negative value for K. Now we're going to store that with the store button. Use the alpha and the left parenthesis for K. So now that's stored for good. Okay, so we'll go back and look at our situation. And now what we want to do is solve for the time at which the temperature was 100. Okay, so I'm going to let the Y value be 100 now, equals 60 plus 290 e to the, now we know the value of K, we're actually solving for the T this time. And I'm not going to write that whole expression in for the K. We understand that we know what it is. And so we'll subtract the 60 from 100 and get 40 this time, equals 290 e to the KT. We're going to divide 40 by 290, and I'll divide out the tens again, so it'll really be 4/29 equals e to the KT. Now don't forget, we're solving for T, not K. We already know what K is. So the next two steps are similar to before, though. We'll take the natural log of 4/29, and then we'll divide by K this time. So T is going to be the natural log of 4/29. Then we're going to divide that by K. And again, we'll do all that from the calculator, right? So we'll bring this up. And we'll take the natural log of the quantity 4 divided by 29. And we can just hit divide by, bring up K. There it is, 27.2 minutes. So we'll call that 27.203. And we'll put that in right here. Now everything was in minutes in this problem. Now I hope you caught this. This really isn't the answer to the question if you read it carefully, because it says how much longer will it take. Now that implies longer meaning after it had already passed the 200 degree mark, right? So it went from 350 to 200 in 10 minutes. Now we're asking how much longer until it gets to 100 degrees. So to answer that question, we really want to answer in terms of time after the first 10 minutes. So the answer to this question really, I'll put in the box over here, the answer to the question really is 27.203 minus the initial 10, leaving you with 17.203 minutes, extra minutes. Okay. Now notice this does follow, it kind of does follow what the law is saying. As the object cools, it takes longer to lose temperature. So it dropped 150 degrees in the first 10 minutes. But to lose the next 100 degrees, which is actually less than the temperature drop during the first 10 minutes, it took a lot longer. Okay, it took 17 minutes and only dropped the next 100 degrees. Okay, so the rate at which it cools is decreasing also. So we do have another example for us to try, but instead of me working it out, I think what I'd like you to do here is, if you'd like to take a few minutes, I'll give you the answer to this problem. It says we're going to repeat the last situation with these changes. The room temperature will now be 70 degrees. The object will this time cool from 120 degrees to 100 degrees in the first 15 minutes. And the question you want to answer is, how much longer will it take to cool to 80 degrees? Now, the answer is 32.26 more minutes. If you'd like to try for practice, just try and work it out yourself and prove that that's the answer. You'll be feeling pretty good, and you can go try the last couple of problems on today's assignment sheet. I hope this helps, guys, and we will talk to you soon.